Directional derivatives. The directional derivative of f in the direction of u is d sub u of f of x0, y0 is equal to the limit as h goes to 0, f of x0 plus ha, y0 plus hb minus f of x0, y0 over h, where u with components a and b is a unit vector. So the directional derivative of f in a given direction is a generalization of the partial derivatives that we already know. The partial derivatives are actually directional derivatives in two specific directions. So for example, d sub I, where I is the vector with components 1, 0 of f at x0, y0. Notice for I, we're replacing a by 1 and b by 0, and we get exactly the definition of the partial of f with respect to x at x0, y0. Similarly, if we let the unit vector be j, then the directional derivative of a function f in the direction of j is precisely the partial of f with respect to y at x0, y0. In practice, we use a theorem which says that we can compute the directional derivative of f in a direction u with this simpler computation than what's given in the limit definition. We can simply take the two partial derivatives of f with respect to x and y, and we can compute f sub x at x0, y0 times a, meaning the x component of the unit vector, plus f sub y at x0, y0 times b, the y component of the unit vector. Another way to write this is as del f of x0, y0 dot u. That upside down triangle can be read del. It's the Greek symbol known as nabla, but we usually pronounce it del. And del f means the vector whose components are the partial derivatives of f. The first component is the partial of f with respect to x, and the second component is the partial of f with respect to y. This is known as the gradient of f. So in the future, I'll probably read del f simply as the gradient of f. In other words, a nice way to compute the directional derivative of f in the direction of a unit vector u is by taking the dot product of the gradient of f with the unit vector u. Let's try some examples. Now's a great time to pause the video, try these examples yourself, and then resume the video to check your answers against mine. First one, let f of xy equal x times y, and u equal the square root of 3 over 2i plus 1/2 j. Find the directional derivative of f in the direction of u at 1, 2. Notice that u is actually a unit vector, so we can use it directly in the main theorem to do this computation. So the gradient of f at xy is, once again, the vector whose components are the partial derivatives. The partial of f with respect to x is y, and the partial of f with respect to y is x in this case. Now, the gradient of f evaluated at 1, 2 is then 2, 1. We're replacing x by 1 and y by 2. So the directional derivative of f in the direction u at 1, 2 is the gradient of f at 1, 2 dot the unit vector u. So that's 2, 1 dot root 3 over 2, 1/2. 2 times root 3 over 2 is root 3, and 1 times 1/2 is 1/2. So we get root 3 plus 1/2. Next example, find the directional derivative of f of xyz equals x squared y minus yz cubed plus z at 1, -2, 0 in the direction of the vector v equals 2, 1, -2. Two things here. Number one, we didn't actually define the directional derivative of a function of 3 variables, but hopefully you can understand that it generalizes in the expected way. Second, and more importantly, the vector v is not a unit vector. So we're going to need to normalize that vector first before we could use it in the theorem to compute the directional derivative. So first, let's find the length of v, which is the square root of 2 squared plus 1 squared plus the square of -2. 2 squared is 4, 1 squared is 1. The square of -2 is 4. That adds up to 9. The square root of 9 is 3. So a unit vector in the appropriate direction is v divided by its length, which is the vector 2/3, 1/3, -2/3. Next, we compute the gradient of f. In this case, the gradient of f has 3 components: the partial of f with respect to x, the partial of f with respect to y, and the partial of f with respect to z. The partial of f with respect to x is 2xy. The other terms are 0. The partial of f with respect to y is x squared minus z cubed. The third term becomes 0. And the partial of f with respect to z is 0 minus 3yz squared plus 1. Now we plug in the point 1, -2, 0 into the gradient to get 2 times 1 times -2 is -4 for the first component. 1 squared minus 0 cubed is 1 for the second component. -3 times -2 times 0 squared plus 1 is 0 plus 1, which is 1 for the third component. Now, to get the directional derivative of the function in the direction of u, we once again take the gradient of f at 1, -2, 0, and we dot it with the unit vector u that we just found to get -4, 1, 1, dot 2/3, 1/3, -2/3. And that comes out to -8 plus 1 minus 2 all over 3, which is -10 plus 1 or -9 over 3 or -3. Next one, find the directional derivative of f of xy equals 2x squared y cubed plus 6xy at 1, 1 in the direction of a unit vector whose angle with the positive x-axis is pi over 6. So once again, the gradient of f is the vector consisting of the partial derivatives. In this case, the partial with respect to x is 4xy cubed plus 6y, and the partial with respect to y is 6x squared y squared plus 6x. Plugging in 1, 1, we get 4 plus 6, which is 10 for the first component, and 6 plus 6, which is 12 for the second component. The unit vector we want, remember, is cosine pi over 6, sine pi over 6, which is √3 over 2, 1/2. So to get the directional derivative of f in the direction u at 1, 1, we just take the dot product of the gradient of f at 1, 1 with the unit vector u that we just found. So that's 10, 12 dot √3 over 2, 1/2, which comes out to 5√3 plus 6. Once again, our main result from this section is that the directional derivative of f in the direction u at x0, y0 is the dot product of the gradient of f at x0, y0 and a unit vector u. By our main theorem on dot products, we can rewrite this as the length of the gradient of f times the length of u times cosine theta, where theta is the angle between the gradient of f at x0, y0 and u. And since u is a unit vector, the length of u is just 1, so this simplifies to the length of the gradient of f times cosine theta. Now, remember from basic trigonometry that cosine theta is always between -1 and 1. Multiplying each part of that inequality by the length of the gradient of f, we get negative length of the gradient of f less than or equal to the length of the gradient of f times cosine theta, which we just saw is the directional derivative, less than or equal to the length of the gradient of f. What this shows us is that the length of the gradient of f is the maximum value of a directional derivative. and it occurs when theta is equal to 0. In this case, the unit vector u and the gradient of f are in the same direction. Similarly, the negative of the length of the gradient of f is the minimum possible value of the directional derivative. It occurs when theta is equal to pi, and in this case, the unit vector u and the gradient of f are in opposite directions. The gradient of f points in the direction f increases most rapidly, and the negative of the gradient of f points in the direction f decreases most rapidly. Let's try an example. Go ahead and pause the video, try this example yourself, and then resume the video. Let f of xy equal x squared e to the y. Find the maximum value of a directional derivative at the point -2, 0, and find the unit vector in the direction in which the maximum occurs. Well, the gradient of this function has components 2x e to the y and x squared e to the y. Plugging in -2, 0 into the gradient, we get 2 times -2 e to the 0, which is -4 times 1, or -4, and the square of -2 times e to the 0, which is 4 times 1, or 4. The length of the gradient of f at -2, 0 is the square root of the square of -4 plus the square of 4, which is root 16 plus 16, or 4 root 2. This is the maximum value of a directional derivative at -2, 0. A unit vector in this direction we get by normalizing the gradient of f. We can normalize the gradient of f by dividing the vector -4, 4 by its length, which is 4 root 2, and that comes out to the vector -1 over root 2, 1 over root 2. This vector is the unit vector in the direction in which the maximum occurs. Let w be the function capital F of x, y, z. The gradient of capital F of x0, y0, z0 is normal to the level surface at the point P, x0, y0, z0. Therefore, we can write an equation of the tangent plane to the surface at the point P with coordinates x0, y0, z0 as the partial of capital F with respect to x at x0, y0, z0, x minus x0, plus the partial of f with respect to y, x0, y0, z0, times y minus y0, plus the partial of f with respect to z at x0, y0, z0, times z minus z0 equals 0. Notice that this is just an equation of a plane passing through the point x0, y0, z0 with a normal vector whose components consist of the 3 partial derivatives. Let's try an example. Go ahead and pause the video. Try this example yourself first, and then resume the video. Find an equation of the tangent plane to the ellipsoid x squared plus 4y squared plus z squared equals 18 at the point 1, 2, 1. So we'll call capital F of x, y, z x squared plus 4y squared plus z squared. Then the gradient of f at x, y, z is 2x, 8y, 2z. And if we plug the point 1, 2, 1 into the gradient, we get 2, 16, 2. So we can write an equation of the tangent plane as 2, that's the x component of the gradient, times x minus 1, the x coordinate of the point, plus 16, the y component of the gradient, times y minus 2, that's the y coordinate of the point, plus 2, that's the z component of the gradient, times z minus 1, the z coordinate of the point, equals 0. Also, we could use the same information to find an equation of the normal line to the same ellipsoid at the same point. Go ahead and pause the video and try and write an equation of the normal line, and then resume the video to check your answer. So once again, I'm just rewriting the same information. Capital F is the expression x squared plus 4y squared plus z squared, and we have the gradient here at the point 1, 2, 1. We can now write an equation of the normal line. We use the point 1, 2, 1 and the vector 2, 16, 2 to get x equals 1 plus 2t, y equals 2 plus 16t, z equals 1 plus 2t.